title is Deep Formal Methodology for ARM Austin's A-Class CPUs, Evolution and Learnings. Vikram has a bachelor's in engineering from BITS, Pilani, and a master's in computer engineering from the University of Minnesota, Twin Cities. Vikram currently leads the CPU formal verification team at ARM in Austin. So over to you, Vikram. Thank you.
Thank you. Thank you, Mike. Hi, everyone. I'm going to be providing an overview of the evolution of our formal methodology over the past few years, and maybe provide a few learnings that we've picked up along the way. So let me get started. So this is sort of the outline of the talk. We'll talk a little bit of history. We'll go into the scope of our effort for a major CPU project that we started a few years ago. Talk a little bit about methodology. Also discuss how we engage with designers, and a little bit about infrastructure and flows that we developed. Some discussion of results, and a little deeper discussion of challenges that we faced. And then the second part of the talk is basically looking ahead and what kind of lessons do we draw, and how we went back to the drawing board and rethought our strategy, came up with a new roadmap for where we want to see formal going, and then some of the more tactical changes that we applied to the next project, and finally some concluding thoughts. So a quick glance at our history. We started late 2013, just a couple of guys, myself and Bebel, who's going to be talking right after me. So we did some initial work on the Cortex A57 and 72. These were both mature products at the time. We got some help from internal formal experts from other sites in ARM. We developed some, we inherited some homegrown methodology, and we also developed some. We piloted some formal test benches on a few blocks. Again, the idea here was to learn as much as possible without actually having any real expectations of delivery. And then we went ahead and in late 2014 we started we sort of mounted a more serious effort with formal on the current generation Cortex A CPU. Again, it was a very ambitious effort, and management support was absolutely critical to sort of sign off on this. We targeted most of the key units in the CPU for sign off, and I'm going to talk a little bit about that later on. And we did get some initial help from OSCE Technology, which is a formal consulting company out of the US, to kind of help us bootstrap. And we also, essentially along the way, we built up a small dedicated formal team, as well as matured several of the flows and methodology, etc. So, as I briefly mentioned, we started off doing some sort of light or slightly more focused work on A72, and then went on to a more rigorous approach. And basically the idea here is to build more comprehensive end-to-end checkers, which typically require deeper abstractions and a more rigorous approach to signing off on proof depth, etc., and also introducing some coverage and doing some analysis of that. This kind of gives an overview of the scope of the sign-off formal effort. So anything in brown is essentially where we had unit test benches for most of these units. Okay, just one slide on just the overall methodology. So I've kind of split that into three aspects. One is just the base functionality and the safety aspects of the formal test bench. So obviously you require a fairly comprehensive set of interface properties if you are to try to completely verify a block. and using them as both constraints and assertions and neighboring blocks, etc., and then qualifying them with each other or in a higher level environment, be it simulation or formal. And then use of end-to-end checkers we've talked about. Also, managing complexity through abstractions, both initial value abstractions and abstraction models. And then sort of the path to sign off. The main goal there was having no unexplained fails, and doing some serious proof depth analysis for some of the key checkers, as well as some coverage analysis. This slide kind of shows a sample set of milestone goals that we had for each of our project milestones. I'm not going to go into a lot of detail, but just wanted to kind of illustrate this. Okay, quick couple of slides on how we engage with designers. The first part was enabling them. So we developed a library of macros to help them to make it easy for them to write embedded properties. Also help them with, defining the interface properties. Again, we tried to keep it very flexible and not having them to develop all the properties themselves. Instead, we were fine with them expressing a lot of these properties in comments in the RTL, and we went ahead and transcribed those to properties. Also provided, some training and demonstrated the capabilities of the tool, etc., and also with debug, allowing them to debug more effectively. In terms of their involvement, by far the most common model was what I call the medium, where they most of them wrote fairly good set of embedded properties and some interface properties, and then some more or less reactive counterexample debug whenever we presented fails to them. And then there were a few users who went a little further and actually used the formal test benches for bring up and debug. And of course, we needed their inputs for things like coverage analysis and analyzing checker depths, as well as developing some of the more, some of the abstractions that required fairly in-depth microarchitectural knowledge. Infrastructure, we had a very simple flow around the Jasper Gold tool. We had a little Ruby front end, and it sat on top of a bunch of data tickle scripts, and there was a sort of a common phasing flow for the various functions and configurations of the tool. And then we also leveraged a few common scripts from other parts of them. Again, in terms of flow development, as I already mentioned, inherited some homegrown flows, and also picked up a few flows, especially on the methodology side from OSCE. We also ended up developing some custom flows that were developed in-house or in collaboration with vendors. And this included some debug hunting flows, and there's one for equivalence checking. I have a slide on that in a minute. The equivalence checking flow was primarily floating point focused. We started off with RTL to RTL equivalence with older ARM designs, and then we shifted to a C to RTL approach, where we initially used internal performance models and eventually shifted to writing some more custom C models that were sort of structurally similar to the RTL, and made it easier to actually theorem prove them with ACL2. We hired an ACL2 specialist who basically came up with this flow. This flow has largely replaced simulation as the primary vehicle of verifying floating point. Results. Excuse me. So we found a number of RTL bugs. The majority of them were found pre-alpha. Again, there was a slow but steady trickle. After through beta and through the following milestones, but most of them were found pre-alpha. But more importantly, Formal gained mindshare and sort of overall acceptance within the design team, and there were a few people engaged more deeply, but overall, I think it was recognized as a viable vehicle of verification. We also, as I already mentioned, we also replaced simulation as the primary flow for floating point designs. And at the same time, we built a fairly capable formal team and well acquainted with the sort of state of the art and formal. And also, since we spread out across the CPU with some domain expertise throughout the design. This slide shows sort of the distribution of bugs. No surprises here. Sort of the memory system tends to be the more buggy area, as well as fetch, and so that sort of reflects it was no different for formal. In terms of what kinds of bugs were found, again, they were found at all levels of checking, all levels of sort of interestingness. And in some cases, we had designers kind of focus on certain areas of a design and sit in a tight loop and fix their own issues. And of course, they were not tracked anywhere. And then in terms of how they related to simulation, I've sort of bucketed them into three categories. One, where we were ahead of simulation, the feature or the bug wasn't being either stimulated or checked. And in some cases, it was hard to tell whether simulation would have eventually found it or not. So I call it a theoretical race, where it wasn't either sufficiently exercising or it wasn't quite getting to some of those corners yet. And there were a few isolated cases where stimulus was completely turned off, obviously unintentionally. Okay, talk a little bit, a little deeper discussion of challenges. So in general, so the value proposition that we started out with for formal was that formal was capable in many ways and also had inherent efficiencies, which would, arguably compensate for the limited resources we had, both in terms of people as well as compute. And the idea was that there was no need to craft elaborate stimulus, which took up a lot of time for verification. And also that we could start off kind of relatively unconstrained and then build as needed. And of course, there's, the other well-known, advantages of formal. Formal provides very short, simple traces, which should help productivity. There's some cross-fertilization with simulation. We help simulation helps us. And then also we've got several powerful features in terms of visualization and doing what we call Y analysis. However, the reality, in reality, I think there were things turned out slightly differently. It turned out that designers didn't really care for some of these extreme corners while they were bringing up the design, certain basic features. Also, in some cases, building sort of this counterexample guided constraints turned out to be quite noisy and quite time-consuming for some of the more complex interfaces. In retrospect, we could have started out, with a higher degree of over constraints. And also, in terms of, I think there were some trade-offs to be made when, given the fact that we were also trying to maintain some of these properties in simulation, which was basically a requirement. However, there was definitely an overhead to both, to formal as well as simulation because of that. And then also turned out that, things that were required as constraints in formal weren't necessarily very valuable as checkers in simulation in a few cases. And then finally, given that there was no easy way to manage the kinds of failure modes we're talking about, given that things were relatively unconstrained, that just the debug bandwidth itself became a bit of a bottleneck. Given that, especially given that we had less resources. Some technical challenges, again, interface complexity comes up again and again. Some interfaces, especially between the core and the memory system, were hard to constrain. There was a lot of tracking code which slowed down builds, brought down proof bounds, etc. And then there were a few other interfaces which sort of tended to degenerate and became very volatile and just became hard to model. And for some of the initial value abstractions, again, there was kind of a tangled web of dependencies across some of the structures we were trying to abstract, and that potentially can become bothersome, and in some cases we had to replace them with simpler abstraction models. And also there were a couple of things about formal coverage. One was that there's no any kind of bug hunting engines don't contribute to formal coverage in any meaningful way. At least didn't at the time. So that was a bit of a trade-off, whether we should focus on coverage or keep hunting for bugs, or focus on hunting for bugs. And also there were some artifacts in the coverage tool itself. Okay, looking ahead, what are some of the lessons we drew? The main lesson really was to kind of focus, find out early on, identify what areas of design are fertile, are really very fruitful for formal to focus on, put most of your resources there, and that translates to increased debug bandwidth as well. So that means you find bugs, find more bugs faster. And also the level of the hierarchy you apply that is quite important. Again, it sounds fairly obvious in retrospect, but it just helps to keep that in mind. What else paid off? I think some of the units that we did more rigorous grounds-up planning for, that helps quite a bit. Investing in tools and flows early was good in terms of being more productive early on. The other thing that we found out was that I think there's a slight danger of if you've got lots of thousands of embedded assertions, there's a slight risk of spending most of your effort trying to clean those out, as opposed to some of the more higher value end-to-end checkers, where you can, I think, if we had been a little more, sustained, had applied some more sustained focus on those, I think that might have been more efficient. And then also constantly identifying, at each step, keep an eye out for what's adding complexity and what can be abstracted. In terms of interfaces, again, I mentioned some of the effort and developing these interfaces and maintaining them was underestimated. And what could have helped potentially have the interface properties be owned, or at least co-owned by some other stakeholders in the team, including simulation. And then also bring up, I think, aggressively over-constraining is a good approach. And then also in terms of when you're trying to prioritize which ones to pick first, right? Pick the interface constraints first over checkers, which can always be, because there's a dependency inherent to that. And also some of the more difficult interfaces, if and wherever possible, try to move the unit boundaries across those. In terms of abstractions, I think one thing that we found out was that there's sort of a Goldilocks zone for these initial value abstractions. If you do them too early, their RTL is not quite stable, and you incur a cost for all the churn that's happening. And but if you do it too late, then there's probably not enough bugs left by that time to justify the ROI. So we went back to the drawing board following this project and came up with a new strategy. The main sort of key things that we came up with was being able to scale the impact of formal resources, integrate them into sort of mainstream flow verification, and also keep innovating, with the design, with the vendors as well as internally. In terms of scaling, 4 key things were making everyone formally literate to at least some degree, establishing sort of formal guidelines, flows that almost anyone can sort of fused them almost to the point of being push button, and creating more of a sort of a unified resource pool for debug, so that anyone can pick up a formal trace and debug just like that. So that was in terms of scaling, and then in terms of integration, again, things like targeting design hotspots where simulation is not very efficient or is clearly insufficient, combining formal and simulation effectively, trading off versus simulation resources. I'm going to talk a little bit about that in a couple of slides. And also tolerate some apparent overlap in some critical areas where diversity is still good. It's still okay to apply both formal and simulation. Skills and resources. We started off with sort of this approach of the formal lead, not directly talking to the unit teams, but have this sort of structure. We're trying to migrate to this this arrangement where the formal lead's involved with more closely involved with the unit RAL leads and as well as the owners. We want to be here where the formal lead is sort of very loosely decoupled with the unit teams, which are formal mature and self-sufficient. So we made a few tactical changes on the follow-up design. We targeted a few critical areas of changes, for example, the instruction fetch trace cache, which Web is going to talk about in a bit. We did formal only bring up for some key features, which worked out fairly well, and we found issues, and that was appreciated. And overall, we had a very tight sort of integrated planning and scoping effort early on, involving the unit leads, involving the project validation leads. This was also the first time that formal became visible to sort of mainline project management. And the main thing was that we prioritized formal tasks very highly tuned to what kind of verification problem there is, and what's available in terms of both simulation, what resources are available in terms of both simulation and formal. And also we followed this mantra of, the order of precedence of picking formal was sort of value, then effort, and then look at formal complexity. Again, we focused on, instead of trying to start off under constraint and then progressively over constraining, in some cases, or constraining, we started out with highly over constrained and then start relaxing things, mirroring the features that are being brought up, and that makes it a lot more manageable. And then also not necessarily tying the interface assertions and simulation bring up at the hip, allowing some lag there. I think that helps formal definitely. And also focusing on bug finding from day one. Don't blindly chase progress in metrics, but look at sort of anything that helps find bugs earlier. Again, complexity reduction, bug hunting techniques, et cetera, et cetera. And also encouraging designers to write some interesting covers early that help with bug finding as well. And this is a slide on just kind of how we revised some of our flows, things that we didn't do before in the previous project for various reasons. Adding formal unit smokes, regressions, and continuous integration, and also creating this very clean debug handoff flow where it just makes it easy to bundle up a fail and pass it around to whoever needs to debug it. So slide on to results. So results from the new application of our updated methodology. I think clearly we had a good impact on project schedule and quality. The project came out, again, ahead compared to the past projects. We like to think in no small part due to formal. We helped clean up some key areas, faster, and also we got larger team more involved in terms of using formal as well as contributing to it. Some of the future efforts, again, we're going to keep pushing integration, as we talked about earlier, keep training more people on formal. We're also coming with this idea of having sort of sub-teams within verification teams, which are dedicated to doing microarchitectural exploration. Again, formal is a very critical part of that scheme. And also evolving sort of the coverage metrics and sign-off requirements for this now, where you're doing certain things with simulation, certain things with formal, and certain things with both. And more recently, functional safety has become a area of focus, and we're trying to make it a formal only verification effort. Concluding thoughts, so I think formal, in terms of performance and adoption, I think we've come a long way, but we have a long way to go still. There's a lot of room for growth in terms of the underlying technology, usability of formal, as well as just the methodology. And there's also, sort of more organizational work remaining to be done. That's all I had, actually. So I'm not sure if we have time for questions. I think I went a little over.
Yeah, we do have time for a couple of questions.
Okay.
Any questions in Bristol? We have some questions online, I think.
What?
Yeah, we have a question online. How did you focus on early relevant logic? What was the process?
I'll tell you, how did you focus on?
On only the relevant logic. Sorry, I may have mispronounced that. How do you identify only the relevant logic, basically?
So how did you identify relevant logic? I'm not sure I understand.
I guess he's asking which bits of the design you focus on for formal.
Right. So I think I think we look at just historical analysis of typically areas that are buggy and take a long time to get clean. And again, any amount of concurrency in high concurrency areas where there's a lot of more asynchronous events going on, I think that tends to be good areas for formal. And there's also areas, for example, in things like encoders, decoders, where there's tons and tons of combinations, just combinatorially complex, where simulation is going to have a hard time reaching all the different cases.
Okay, another question online is how many checks as a percentage of overall checks do you achieve foolproof?
How many checks? Oh, I see. Okay. Yeah, that's
checks do you actually
right, foolproof. So that tends to be roughly, I would say, anywhere from a ballpark, like on a given, on average for units, around maybe the 40 to 60% somewhere. It doesn't usually end up being, anywhere higher than that. However, we do have a sort of more bounded proof methodology where we actually, I had a slide on that, I just didn't have time to share it, where we have a methodology in place to, once we have, reached a, the first threshold is looking at the associated witness cover for a given checker. And if we've gone past the depth of the witness cover, that's the one level of confidence. That means we've explored past that. And then we look at things like we add additional covers, talk to the designer, look at simulation failures, et cetera, et cetera. I think there's many ways you can analyze a bounded proof and give yourself confidence that that's enough, that's sufficient.
We've got time just for one more question, I think, because we're running out of time. And this is a question about what types of bugs you found. Were they specification related, microarchitecture related, or I guess the other one might be implementation related?
So I think they were mostly microarchitectural. I think in a few cases we did find a few more architectural ones, but they were fairly rare. I think it was mostly microarchitecture.
Okay, there's a few more questions. I think we're out of time, so thank you very much for your talk, Vikram. Very interesting.
Sure, thank you.
Good luck continuing your journey. So, thank you.
Thank you.